Hey everyone, welcome back. I'm Andrea and I'm a member of the Elixir core team. This is the 9th and final video of this series I'm making on network programming in Elixir, where we solve challenges from Protohackers.com. So the reason this is the last video of this series, even though Protohackers still has challenges coming out, is that I don't really know that there is much left for me to showcase in this specific format about networking in Elixir. This is not my last video in general though, so if you have topics you'd like me to talk about, or formats you'd like to see on my channel, or that you'd like me to explore, just leave a comment below. In this video we'll build a TCP server that talks with its client through an encrypted layer. It's more like data mangling than encryption, but the point of the problem is to simulate encryption. We'll also stop rolling our own TCP pooling code and use an existing library instead that provides abstractions to build TCP acceptor pools. So enough intro talk, let's dive in. This problem is fairly simple in my opinion. We're building a TCP server where clients are completely isolated from each other, so there is no need for global state or cross-client communication, which makes the problem simpler, I think. Clients connect and tell us information on how they want the data to be encrypted. After that, they communicate with the server through a sort of encrypted line-based protocol. The application itself is just that simple. For each client request we get, which is a line, we send a response. The request contains a bunch of toys with numbers associated with them, and we need to essentially parse this line, find the maximum number, and return it, more or less. That's just it. So let's look at the encryption layer, which should be the focus of this problem. This protocol has the concept of a cipher. A cipher is a series of byte-level operations to apply to each incoming and outgoing byte. There are a handful of possible operations that can make up a cipher. We have reverse bits, which reverses the order of bits. Then we have add, which adds a number modulo 256 to the byte so that it stays a byte. Then we have XOR, which performs an exclusive bitwise OR between the byte and the given number. So let's also clarify what XOR is. An exclusive bitwise OR returns 1 if the two arguments, the two bits are different, and returns 0 if the two bits are the same. So then we have add pos, which adds the position of the byte in the stream, modulo 256 again to the byte, and then we have XOR pos, which does the exclusive bitwise OR, the XOR of the byte with its position on the stream. And then we have this thing which they call cipher spec, which is a way to encode a cipher. So a cipher is made of a bunch of these operations that we just described, and each cipher operation is identified by 1 byte in the spec, and then add and XOR also are followed by a byte for their argument. We know when the cipher ends because there is a 0 byte at the end that tells us that the cipher has ended. And cool, I think that's a great place to start writing some code, so let's do that. So let's start from parsing the cipher spec from its binary representation into a list of Elixir terms. Should be pretty easy to do. First, we can define a dialyzer type for the spec itself. Just a disclaimer, I often don't even run dialyzer itself because it's like, it can be, you know. But I like to use specs to kind of as concise documentations. Okay, let's start with writing this type. Let's call it spec, even if it's an overloaded term. And we said the ciphers can be either reverse bits, we'll represent it as an atom, or it can be XOR with a byte, or it can be XOR position. This should be a pipe thing, or it could be add with a byte, or it could be add position. And we got ourselves a type. Okay, now let's write a parse spec function. So let's write the spec first, because again, it's a little bit easier for me to reason with like this sort of documentation / types. And we'll say that this parse spec function takes a binary and it returns okay, a spec, where we just define this type, and then a binary. Or it returns just error. And the reason that this binary here as the third element of the return tuple is there is that we want to return whatever is after the zero byte, essentially the final byte. And this is kind of helpful to avoid having to do this part in the connection handler, as we'll see later on. So it kind of simplifies our life a little bit. So I will write this function as parse spec. It takes a binary, or like a spec, let's just take a binary, when is binary, that's great. And then let's just do a recursive function where we call parse spec, and then we store all the things all the ciphers that we parse in an accumulator. Okay, and I'm gonna paste in this function. Actually, let's write the first clause. So I'm gonna write something like parse spec, and I'm going to say if I get the 0 byte, and I'm using hex notation because that's what they use in the problem description. It's a little bit easier to reason about. And then whatever else I have left, and I have an accumulator after this, then I can return, okay, enum.reverse the accumulator, because we append at the beginning, or we prepend to the accumulator, as you'll see in a second, and then whatever is left. And then let's write another clause because it's fun, and we can say parse spec if we get 0x01, which is this, and then something else, and this is the byte representing the reverse beats cipher. So we keep doing recursively on the rest, and we add reverse bits to the accumulator, and we keep going. And now I can paste the whole implementation and remove the first two things here, and you can see it just does exactly the same thing. When we have a byte after the cipher, like XOR takes an argument essentially, and add takes an argument as well, we just take another byte from the binary, we match another byte from the binary. And this implementation should work. For these simple pure functions, I often like to write, I like to write tests, but I often like to just write doc tests as the only tests. So let's just do that. I'm gonna write doc here, and I'm gonna say examples. I'll fill this in later, but the idea is that I can write doc tests that say something like ISL.cipher. ISL is insecure socket layer, is the problem that we are working on. .cipher, and I say parse spec. For example, if I parse the 0 byte here, then I should just get, okay, I should get an empty spec, and then I should get a empty binary as the rest. Let's try something else. If I say cipher parse spec, and if I get, again, 0 byte, so the cipher is finished, and then hello. After that, I should get, okay, an empty spec, and then the string hello again. If I get ISL cipher parse spec, if I get, for example, 0x03, or like 02, which is XOR, then 0xAA, for example, any byte. I picked a random byte, then 0x01, reverse beats, and then 0x00, and then hello again. Then I should get something that looks like, okay, then I should have this, my cipher should be XOR with 0xAA, and then reverse bits, and then I should have a low as the rest. Cool. So this should be cool. And then I also want to test it, like, for example, ISL.cipher.parseSpec. If I get the first byte is something that's not recognized, like, I don't know, FF or something, then I should get back error. So this is an error. And I should get back an error also if I get something that is not complete. So for example, I could say ISL.cipher.parseSpec, and I say something like 0x01, which is a valid cipher, but I don't have the end 0 byte that signals the end of the cipher spec, then I should still get error. And I will handle this with buffering, as we've done in previous videos in the connection handler. Cool. So I also created a file here, Cipher test, to test this stuff. And I do still need a file, like a module to test these. And I'm going to do something like ISL.cipher test. And what I'm going to do here is xunit.case async true as usual, and then I'm just going to use the doc test macro. So I say doc test isl.cipher, and this should be enough to actually test this stuff. So, and then if I try to run this, so I say mix test this thing. Okay, there's a bunch of stuff that we haven't implemented yet, but it's fine. But the idea is that all the doc tests pass. Fantastic. Next, let's write a function to actually apply the cipher spec to, or quote unquote, again, encrypt a binary. So we're going with doc tests here again, and let's write them first and make them pass. Let's take sort of a TDD approach. So, and these examples that I'm going to write are mostly taken from the Protohackers description. So I'm going to say something like IX, for example, ISL.cipher.apply, which we'll write in a second. And if I say hello and I apply XOR with 1 and then reverse beats, and then another number that we'll talk about it in a second, then I should get back something that's like 0x96. I'm obviously reading from notes. I don't know this by heart, how to do XOR and reversing bits. 0x B6, 0x B6 again, because it's an L, 0x 7, 6. Great. So the number that I have here is essentially the start. It's the start position. It's a parameter that our function is going to take, and it's there so that we can correctly apply the add pause and XOR pause ciphers which require the position of the byte in the stream. Right, so we're passing that in so that we don't have to keep any state in this module, and just makes things simpler. I'll also write a spec for this function. So it's going to say apply, and it takes a binary. It takes a spec, and it takes a non-negative integer, which is the position, and it returns the encoded binary. And then I'm going to say, let's apply this, and it takes data, it takes a spec, and it takes a start position. And what I'm going to do here, I'm going to use four binary comprehensions, which we've done once in a previous video. So again, I never use them, but they're pretty fun. So I'm going to say for every byte in data, and I'm going to reduce on a tuple that contains essentially the accumulator for the end result, for the encrypted result, and then the start position. So we're going to keep the position going and incrementing it by 1. Then I'm going to say, so for this, I have a clause, just a single clause that contains the accumulator till now and the position till now. And this is also nice because we have never used four comprehensions with reduce in this series. So it's nice to use. And so for every byte in the input, what we do is we say that the encoded byte is equals to enum reduce. And we reduce over the spec. So for each byte, we apply every cipher in the spec to the byte. We start with a byte. And our reduce function is, let's call it apply operation. And it takes the current byte, the current operation, and then the current byte, which is the accumulator for the reduce. And it takes the position because it's always the same for that byte. And then we return here, the new accumulator is the accumulator with the encoded byte after it, and then we increment the position by 1. So this all 4 is going to return the encoded, and then the final position, which we don't really care about because it's going to be exactly start position plus the size of encoded, so we don't need to return it from this function, and we can return encoded. Okay, so this looks good. We need to write this apply operation function. So I'm going to go with apply operation. For example, reverse, actually that's a bad one to start with. Let's start with XOR n and byte, and it doesn't depend on the position. So we're just going to ignore the position. And this is actually bitwise. The bitwise module has a big XOR function, which we can use. So we just say n byte. So we just XOR n with the byte. Perfection. And the other ones are pretty similar. So for example, if I say apply operation, let's do like, I don't know, add the position to the byte. And it takes, like we care about the position 2 here. In this case, we do byte plus position, and we do the remainder of this with 256 so that we keep a byte. And I will paste in the rest. I will also import bitwise here so we can use big XOR. Okay, and I've pasted in the rest. It's looking pretty straightforward, and we're just doing the same sort of operations. The only one that's not super that we haven't defined yet is this reverse bits thing. And the reason for that is that there's no built-in function that I know of to reverse bits of a byte. So we're going to write our own. And I like to put it as a public function here because I can test it, since I'm doing an implementation of it. Reverse bits takes a byte. I'm going to paste in the implementation so that you don't have to look at me type it. But essentially what we're doing is we're constructing a binary with only that byte. And then we're using binary pattern matching, or like this, in this case, bitwise pattern matching, so that we can extract every single bit of it, from B1 to B8. And then we say, okay, we construct a binary from the bits with the bits reversed, so B8 to B1, and then we match on an integer in there or a byte in there, and we return the byte so that we get an integer, we return an integer. If we were mangling with binaries, we would not need this like whole thing. We would just reverse the bits and that would be fine. But we are extracting, like constructing a binary and then extracting the integer in it. And this syntax with the colon 1 is like a bit the length of in bits of what we're matching. So if we said, hey, 8 here, it would be a byte, for example, but we say 1 because it's a bit. So this should work. I'm going to write another doc test here because that's what we're into in this video. And I'm going to say isl.cipher.reverse bits. If I pass 0b, 1, 2, 3, 4, 5, 6, 7, 8, then I should get 1, 1, 2, 3, 4, 5, 6, 7. So I should get exactly the opposite. And I don't care about other cases. Let's just pretend it's fine. And if I run it again, so it passes again, that's great. And also our apply function, I forgot to run tests, but our apply function passes as well. So, okay, we are almost done. One more thing to do is that the problem description says that the server should apply the reverse of the Cipher spec to decode incoming data from the client. So essentially, the client sends us encrypted data that it encrypted using the Cipher spec that it describes. In order to decrypt it, we need to use the reverse of the Cipher spec. So we're going to write a reverse spec function, reverse spec function, which takes a spec and returns a spec. Let's actually spec these functions. Oh my God, I'm saying this so much. So this takes a spec and returns a spec. And I can write a spec for this function as well that takes a byte and returns a byte. Perfect. So our reverse spec function, let's try to write a doc test for it first as well. And we're going to say isl.cipher.reverse spec. So for example, if I have a spec that's like reverse bits, then I have XOR position, then I have add position, then I have XOR 3, and then I have add 9. Then I want to say this should return. So actually, this is a first problem. What's the reverse of, like, we need to do the reverse of this list. So we need to go from right to left. Sure, but then we also need to reverse every single operation. The good thing is that XOR is the inverse of itself, so we don't need to actually reverse XOR, but adding is not the inverse of itself. And reverse bits is the same. If I reverse the bits twice, we get the same byte back, but add is not the way. So if we have add, we need to have the reverse of adding, which is subtracting, right? So I'm going to introduce a pretend operation here, which is sub instead of add. So I'm going to say sub 9. I'm expected that this returns sub 9. Then XOR 3 should be the same. Then the same for adding a position. I should have something like sub pos, where I subtract the position. XOR pos stays the same, and reverse bits also stays the same. And if I try to run tests now, this should not pass, hopefully. Yes, that's perfect. And also one more thing to do is that I need to add this sub byte, and trust me, I'm writing behind my face. Nope. Okay, I'll move it. Okay, sub position here. Okay, so the spec is good, is updated. And also we need to apply the corresponding operations, right? So for example, or I guess I'll do this. If I say sub, this just turns into a minus. And if I say sub pos, this just turns into a minus. And I should be good with that. So I have the reverse operations, and now I need to actually reverse this thing. And what I'm going to do is I'm going to say, take the spec, actually reverse the order of the list here. And then I map over each single thing, and I say, if this is add pos, then use sub pos instead. If this is add n, then use sub n instead. Anything else stays the same. We say because XOR and XOR pos and reverse bits are the reverse of themselves. So this should be enough. And if I run the tests, great, they pass now. Then one last thing for the Cipher. This is where I actually spend most of the time to solve this problem, because the problem description says that we need to shut down clients that use the Cipher spec that results in a NOP. That is, the Cipher maps each byte to itself without modification. So it's kind of a useless Cipher. So let's write a no-op function that's going to say no-op. It takes a spec and it returns a Boolean. And it's essentially, this function is going to tell us if the given spec is a no-op spec. So it takes a spec. And I am going to paste the implementation. And now that we got the implementation, we can talk about it a little bit. So the idea is, there are some ideas here that I had to kind of like go through. I'm sure there's a simpler way to do this, but I'm not. I mean, I'm not very good at bitwise operations or just like this sort of stuff. So I just like improvised. And the idea here, for example, some ideas here are that like if there is an odd number of XOR positions, in XOR position, XORs always with a different number. And if there's an odd number of XOR, it means that it should result in something different because two XORs cancel each other. So, or if there's any add pos operation, the cipher can't be an op because add pos is always adds a different position. If all the add operations add up to a multiple of 256, for example, then then those are a no op again because of addition modulo 256. So that's what we're checking here. If total add is different than 0, then it's not an op, otherwise it's an op. And for example, things XORing with a 0 is also an op because it just leaves all the bits unchanged. Then we check whether XORs end up being equivalent to XORing by 0, taking also reverse bits into consideration. So there's some logic over here where we do stuff like, okay, if we get XOR, if we get reverse bits, then reverse all the XORs after. And if we get XORs, essentially take all the XORs all the arguments together, see if they end up being a 0 essentially, and if they do, then like it's not really not doing anything. And so we take a look at all these ciphers and we make sure that we check if they would end up in being an op. I'm not sure this is exhaustive as well, because I'm not sure, I like there's really no way that we would need to mathematically prove that this is a correct implementation, but I just went with like running Protohackers a few times and like seeing what ciphers it was it was giving me, and these all seem to pass their tests, so it's good enough for me. An alternative approach to this would be to test the cipher spec against each byte. After all, I mean, there are only 256 possible values, so it should be fast enough, given a spec, to actually test it for all 256 possible values of the byte and check if any of them is different, the output is different, right? And then it's not an op. But we need to take the position into consideration as well. And in any case, I wanted to try to solve this in like using logic instead of using like brute force, but maybe this was a more straightforward solution, so like exercise left to the reader, I guess. Cool, so the protocol stuff is done. I will not bother writing tests for this. I'll paste them in the implementation on GitHub later. And we also have tests. I mean, we have tests for this stuff through doc tests, so we're good to go. Let's move on to handling our clients and connections. In past videos, we've seen how to roll our own TCP acceptor code and connection pool, so go back to those if you want to get an idea of how to do that. In this final video though, I'll use an existing library instead that provides robust functionality for accepting and handling TCP connections. The library is called Thousand Island and it powers the all Elixir HTTP server Bandit. Another commonly used TCP server library is called Ranch in Erlang and it powers the Erlang web server Cowboy, but I have some reservations on those names, and in any case, the idea behind these two libraries and their APIs are really similar, so it shouldn't matter too much. And the idea with using an actual library in the final video is that this is what I probably do if I were to write something like this for production. I'd probably use a library so that I wouldn't have to get all the edge cases of building TCP acceptor pools and connection pooling to get them all right. And I would instead use a library that lets me write more declarative code and just be easier to work with. Cool. So let's add Thousand Island to the list of dependencies in our Thousand Island in our application. And I'm going to say 0.6.0 is the latest version. And I'm going to run a mixup.get. So the API for a Thousand Island server is quite similar to what we hand rolled in previous videos. We'll start by adding a Thousand Island server to our list of children for the top level application supervisor. So I'm going to go into the application file for this ISL application. We have no children, and I'm going to add a Thousand Island server. Great. I'm going to pick a port, which we'll do in a second, and then I'm going to say handler module isl.connection. Let's do that. And I'm going to say port is equals to string usually do this string to integer, and I get system.get env I put it in the TCP port environment variable, and I default to, I don't know, 5009, I think is the next free one. And this is a string by default so that we can always call to integer in it. So this should work. And this handler module thing, we specify a handler module for the server, which is where we'll define the code that handles this connection. So it's sort of a callback module, right? And so let's go and create that. All right, we have this ISL.connection module that we pass as the handler module. Connection handlers implement the thousand-island.handler behavior. So we can do use thousand-island.handler. And it also calls behavior. So we need to define a bunch of callbacks. And they're essentially a wrapper. These handlers are essentially a wrapper over gen servers with some additional callbacks. So what I'm going to do here is I'm still going to require logger. And the first callback that we'll see is handle connection. So handle connection, which takes a socket, which is a thousand-island socket, which is a wrapper over the TCP or SSL socket. And it takes also handler options, which for us is going to be equals to the empty list, but we can pass this over here in the application. We could pass handler options here to kind of give some arguments to start off the connection handler. And what we're going to do here, we're going to return continue to signal that we want to keep the connection open essentially and do nothing else. And we don't really care about a state, but I'm just going to like put right module in here, and we're going to define a struct in a second, but we won't put anything in it. We're also not doing anything with the socket, and I'm going to also say that this is an implementation. This is just bugging me that there is no struct here, so let's define one for the state. And what this state is going to hold here is the Cipher spec itself. Then it's also going to hold the reverse Cipher spec for a client. So we kind of store it so that we don't have to compute it every time. And the Cipher spec is nil when we start a connection, because we don't really know the Cipher spec of the client. We're going to have to wait for the client to tell us. Now we also store a buffer, which is going to be start empty, and this is where we buffer data as we did in previous videos. And then we store the client position, which we start as 0, and the server position. This is what we use to actually use to apply the XOR pause and add pause ciphers. So we keep the position around. Awesome. The only other callback that we'll implement here is called handle data. So handle data, and it takes some data that we get, some binary data we get from the socket. And the socket itself, again, the thousand-island.socket, and the state that we used, that we returned from previous callbacks. So what I'm going to do here is just going to say debug something here, and I'm going to say this to say like all incoming data, inspect data, and I'm going to say base hex so that numbers are printed in hex representation. It's a little bit easier to debug when the protocol spec is all using hex. And the idea here is that if everything goes well, so we're going to actually handle the data. So we're going to say handle new data, and it takes a state, and we'll pass the socket as well, and we'll pass the data. And we'll write this in a second, but the idea is that if everything goes well, then we return continue state again. So we keep the connection open. If there's an error, we just call close and then the state. Since this is, we're going to write this in a second, since these are connection handlers, as we saw in previous videos, there is really not much sense in doing error handling, because once we close a connection to a client because of some error, then we can't really reopen it because we're the server, right? It's the client that needs to reopen it. So what we could do is like send some interesting error message to the client, but there's nothing like that in the protocol spec. So we just don't do anything. We just close the connection if there's any error with handling the data. So let's go write this function, handle new data. And we said it takes the data, it takes a state, and if the Cipher spec is nil, this is going to behave differently, essentially, if the Cipher spec is nil or if the Cipher spec has already been received. Because if the Cipher spec is nil, we're waiting for the Cipher spec, essentially, right? The client needs to tell us, the first thing it needs to tell us is the Cipher spec. But after we have a Cipher spec, then all communication is encrypted, encrypted. So essentially, any bytes that come in, we need to decrypt it and handle it decrypted, right? So I'll paste in the implementation here. So we're appending the data to the buffer so that what the state now contains, the buffer contains all the data. And then we're calling this parse cipher spec function. And if this can return okay, the state, and then some other binary, and then we call handle new data recursively with the rest of the binary, or if it returns error, just bubble up the error. So the cipher spec function expects a state with no cipher, and it tries to do this parse spec function that we wrote earlier on the data. If this returns a cipher spec, then what it does is it checks if it's a no-op. If it's a no-op, we just log an error on the server just to know, and we return error because this is like effectively an invalid thing, and the protocol says that we should close the client. And then if instead it's a valid cipher spec, we just debug it, and then we put the cipher spec in the state, we put the reverse of the cipher spec in the state, and we reset the buffer because we parsed everything from this cipher spec, and we return okay, state to rest. And then we'll handle the new data here, back here. So now let's write the clause where we handle data once we have a cipher spec. So we handle encrypted data. Okay, I just pasted this in. So if we get new data and we already have a cipher, what we do is we call cipher.apply, which is we wrote earlier, with the client position and the reverse of the cipher spec to decode it. And we say, we log something here, say handling decoded data, blah, blah, blah. And then we update the client position by kind of moving it up from with the byte size of the data. We update the buffer with the decoded data this time. So now the buffer is holding decoded data. And then we call this handle new decoded data function. So we can not care about encryption anymore. Okay, and I pasted this in, this handle new decoded data. This is actually essentially, it's doing the application layer work. It's not very fun or interesting. We're trying to split the buffer on a new line. So if there's a new line, then we actually handle the line. Otherwise, we just keep going and try to parse more lines. Otherwise, we just return. And to handle the line, this is just string, like playing with strings. So we split the strings on commas, and this is like the problem spec. We look at the stuff, we parse the integers, we find the biggest one. And then the only interesting part, I think, is that here we call cipher.apply to actually encode the data, right? So we use the cipher spec to encode the data from the server, and then the client is supposed to do the opposite of what we're doing. So use the reverse cipher spec, and then we use thousandisland.socket.send to send the data on the socket. And this is a wrapper around gentcp send or ssl.send. So we should be familiar with that. Okay, so this is all for the application logic and essentially for our connection handler. As you can see, using a library like Thousand Island simplifies the handling of the connection or the network stuff quite a lot. As you can see, the functions that we have here are really just these two. That's all the handling of TCP connections and closing the TCP sockets. And you have more callbacks here as well, where you could say something like handle close. So if the client closes the connection, then you can react to it, which is equivalent to getting a TCP close message and handling it. But I really like having this, a sort of library like this, because it takes care of a lot of stuff that you need to know, to take care of. So for example, okay, the socket closes, there's an error, or for example, active, non-active, there's a lot of stuff that we need to deal with, and it can be very manual to write a gen server, to handle this stuff, or a state machine or whatever. And instead using a library lets you focus on actually the business logic, right? So you don't go, it's pretty clear what we're doing here. So I think it's a really good addition to your tool set to write network applications. Okay, and last but not least, I want to show you the tests that I wrote for this. I just call them ISL tests here. I don't want to type them out because it's a lot of typing and not a lot of stuff to learn from me typing, but these are just a couple of small integration tests here. I essentially took the example session from the problem description and turned it into a test mostly. So what we're doing here is the usual stuff that we're used to at this point. We're setting up a TCP client to our server. Then we're sending some data from the problem description, and then we're sending some more data. So this is the cipher, this is the encoded data, and then we're making sure that we receive the right encoded response to our request, and again to another request. And then I have another small test here that just tests that no op ciphers result in the client being disconnected. So I connect with the client, I send a cipher that is a no op cipher, and then I make sure that the connection gets closed by the server, so that it behaves correctly according to the protocol. Okay, so let's go try to test this. I have our usual IP and I have the port number for TCP, and I just deployed this a second ago. So let's see if it works. So it's checking stuff, everything seems to be okay. It's trying a bunch of, as you can see, it's trying a bunch of Cipher specs with weird ciphers and everything. And then it's also trying with no op ciphers, like zero length cipher spec, and then all the adding zero, XORing by zero, and then trying like, XOR zero, XOR zero, reverse beats. And then it tries like, starts to try some really weird ones, which I really liked to debug. So for example, you have add zero, and then it interrupted, well, it's passing, but it interrupted our chat. So like, for example, here, you add, where are we? Okay, well, you add zero, you reverse the beats, and then you reverse the beats again. So add zero is an op, reversing beats twice is an op. Then you add 117 plus 9 plus 0 plus 105 plus 21 plus 4. It's probably equals to 256, so it's an op. Then you XOR by 0. Then you XOR by 32, and then I bet that like if you reverse the beats of this and you XOR by all of this stuff, then it essentially also comes to XOR by 0. But it's a long cipher, so it's pretty fun. But yeah, it passes. It checks with 10 simultaneous clients. Everything seems to work. It passes, so great success. All the code that I wrote in this series is on GitHub in a repository that is linked in the description below. It might differ sometimes even significantly from what I've shown in the videos, but that's just because I reworked the solutions and I refactor stuff a little bit, and at some point I split the whole project into umbrella apps. But you can dig through commits if that's something you want to do, to kind of like link them back to the video, to the respective videos, or you can see how I ended up writing the kind of final code for the solutions to these problems. Well, this is it. The Protohackers videos are over, at least for now. I really hope you enjoyed them and got to learn something new. I had a blast working through these solutions and recording these videos. If you have feedback or questions, even on the series as a whole, feel free to leave a comment below. I'm also open to new ideas on stuff to record and upload to YouTube if this is a format that worked for you. So just don't hesitate to reach out if you have any. Thank you so much for sticking with me, and I hope to see you on this channel again soon. Cheers.